Okay, so before we start, I would like to mention that this seminar is going to be recorded and it will be uploaded to YouTube. And also, if you have any questions, please write them in the Q&A, and then I will answer them at the end of the presentation. Okay, so I think I will be starting now. Okay, so welcome everyone. My name is Juan Guzman-Inigo. I'm a lecturer in aerospace propulsion at City University of London. I joined City last November, so I've been here less than 1 year. Prior to that, I was a postdoc at Imperial College London, where I used to work in the group of Professor Amy Morgans. A big part of the results that I'm going to present today were done there. Okay, so the topic, the title of my presentation and the topic that I will be discussing today is combustion noise in future aviation. Oh. Okay. Okay, so this is the outline of my presentation. I will first explain what is combustion noise and why it's important. Then I will introduce some work that we have done recently on how to model combustion noise. And then I will speak about how to reduce combustion noise, and I will finish this presentation with some conclusions. Okay, so let's start with combustion noise. So combustion noise is important in the context of aircraft noise pollution. We know that aviation noise or noise in general can affect human health. It does not only create annoyance, but it also, there are many studies many studies have shown a connection between cognitive impairment, sleep disorders, and an increase in cardiovascular diseases. So it is our responsibility to protect the people living in the vicinity of the airports. But this is difficult, especially because there is an increase of air traffic. So we are expected to double the number of passengers over the next 2 decades. However, noise imposes certain limits in airport capacity. For instance, Heathrow and many other airports cannot operate at nighttime, which means that that reduces a lot the number of flights that they can have. And also they need to limit the number of flights during daytime. So there is a clear economic and social value in reducing aircraft noise. If we could have quieter aircraft, the airport could operate more. And also cities are growing around airports, which means that more population is exposed to this harmful effect. Okay, so for the ones of you, well, first thing to mention is that one of the main sources of noise in aircraft is the aeroengine noise. And the first thing that I will do for the ones of you who doesn't have a aeronautical background is explain very roughly the part of a aeroengine and how it works. In this case, we have a turbofan engine. So the difference with a turbofan is that there is a fan that is used for the propulsion. The important parts that I will describe are the following. So we have a fan. The goal or the objective of this fan is to move air at low velocity. And we know that if we are moving air in that direction, because of the second law of Newton, we are going to create a reaction. We are going to create thrust in the opposite direction. So moving air in that direction creates thrust. Then we have the compressor over here. What happens in the compressor is that we take air and we just increase the pressure. And then we deliver that air with an increased pressure to the combustion chamber, which is here. It's very small, actually. And in the combustion chamber, we mix fuel with the air, and we create a flame. We burn that. What we are actually doing is we are transforming chemical energy into kinetic kinetic energy. Then that kinetic energy is going to be extracted by this turbine. This is the turbine, and it's going to be transformed into work. That work is going to be given to the compressor. It's going to be used to move the compressor, and it's also going to be used to move the fan. So that's how the aero engine works. But in terms of sources of noise, we have a source of noise associated to fan, a source of noise associated to jet. So these two are the most important, we could say, the fan noise and the jet noise. And then we also have compressor and turbine noise and combustion noise. And combustion noise is actually the one that is important for us in this presentation. Something else that I want to mention before we move on is that theoretically, we can show that the optimal performance of a turbofan can be obtained if we have an infinitely large fan. That means we have a very, very, very large fan which moves a lot of air at a very small velocity, and that would be optimal. So that's the reason why recent trends, or well, not just recent, but the trends in aero engines in the last 10, 15 years has been going towards larger and larger fans. And that's, as I'm going to explain now, has some implications in the sources of noise of the aircraft. Okay, so this is a typical, this is a diagram with the sources of noise of a typical turbojet. This is obtained from Safran-Schleckmann. And what we can see here is in blue is jet noise. Well, here we have the frequency. So we see that at different frequencies, different sources are more or less important. But in blue, we have jet noise. Then orange is combustor noise, and green is fan noise. What we can see in the fan are those tones, actually. They are produced by the passing frequency of the blades. And there is also a component of broadband noise. And what we observe is that at low frequency, jet noise is the dominant source. At the high frequency, that will be fan noise. And in the intermediate region, combustor noise is important, is the dominant source. What is happening? I mentioned before that the trend in industry is going towards larger fans. We call that bypass ratio. And the trend is going towards ultra high bypass ratio architectures. And what is the impact of that in noise? So we see that the jet noise will decrease. The reason for that is because the velocity of the jet is going to be reduced, and the noise scales with that velocity. But on the other hand, fan noise is going to increase. Obviously, we have a larger fan, and combustion noise is going to increase. When it comes to fan noise, there is already a lot of research, a lot of technologies trying to reduce that. So I would argue that even if we increase the size, there are a lot of progress, and there are a lot of technologies on how to reduce that noise. So combustion noise, on the other hand, has not received much attention in terms of developing control techniques. So combustion noise could be the next noise barrier for aviation. And that's if we are talking about traditional architectures and traditional fuels. When I say traditional architectures, I say turbofans. But I will explain in a minute the current trends in aviation and how is that going to affect combustion noise. Okay, so at the moment we are in a very exciting moment, and there are two main current trends in commercial aviation. I would say that those two main trends are a push for sustainable aviation and a renaissance of supersonic and hypersonic aviation. So what is happening in terms of sustainability? So in the last 10 years, we have reduced pollution. We have more efficient aero engines, and obviously they pollute less. But the drive of that change, of reducing the pollution, was on the efficiency. We wanted aero engines which were more efficient. Now, however, this is changing. Now the driving objective is net zero. We are in a climate emergency, and we are trying to design aircraft that yeah, if possible, if they could have zero emissions, that would be great, or reduce as much as possible the emissions. What's happening in that front? So obviously we have electrical aircraft. Obviously we change the traditional aero engines. We include batteries or fuel cells, and then we have a lot of small propellers. Obviously, I'm not going to talk a lot about that because obviously there is no combustion there. But there are two other trends containing combustion. We have sustainable aviation fuels. So those are fuels that are synthesized from wastage. It could be human or, sorry, not human, animal or vegetal wastage, or even cooking oil. The idea is that they have very similar properties than traditional fuels, but the life cycle, during the life cycle, there is a reduction of carbon emissions of an 80%. And this is interesting from a combustion point of view, but they are not going to change the structure of combustion much, so they are not going to affect combustion noise that much. However, the last point, carbon-free fuels, is very interesting. Carbon-free fuels are fuels that they don't have basically in their chemistry any carbon atoms. So when we burn them, when we mix with oxygen, they don't produce CO2. And this is great because we have combustion, which is clean in a sense. And an example, well, I would say that the two carbon-free fuels that I know are hydrogen and ammonia, but the one that is pushing, or the ones that is going to be more important, is hydrogen. But the properties of hydrogen are very different, and hydrogen aviation is going to pose many, many challenges. And one of them is going to be for combustion. The combustion of hydrogen is very fast. So we need to change, we need to redesign the combustion chamber of for hydrogen. And in my opinion, hydrogen, the reaction is faster, temperatures are higher, so there is going to be more, they're going to be more propense to generating combustion noise. Then, on the other hand, we have the renaissance of supersonic, hypersonic aviation. Here, we have just two examples, but there are many commercial companies trying to develop new aircraft. We have, for instance, Boom Overture, which is going to be an airplane that is going to fly at Mach 1.7. And then we have Destinus that is trying to develop a hypersonic passenger aircraft that is going to fly at Mach 5.6. And in order to achieve that, they need to use hydrogen afterburner. I think they are they have already demonstrated that. But the thing is that this kind of architecture is completely destructive. These kind of engines are going to be completely different than the engines that we have now. Probably they are going to generate a lot of combustion noise. So in traditional architectures and traditional fuels, as I mentioned before, combustion noise is becoming to be important. But when we move to the current trends in civil aviation, when we move to hydrogen combustion, supersonic aviation, combustion noise might be very, very important. Okay, that's about why we should care about combustion noise now. But what is combustion noise? So we know that unsteady combustions, flames, are a source of acoustic wave. Why is that? Is because they generate unsteady heat release, and that's going to induce volumetric gas expansions, and that volumetric gas expansion acts as a monopole source of sound. And this is actually what we can see here. We see how the flame, here we will have a flame, generate this, it's actually acting as a monopole. And this component of combustion noise is what we call direct combustion noise. There is another component that is called indirect combustion noise that I will explain later. But before I move to indirect combustion noise, I would like to mention that flames, they are not just a source of acoustic waves, but they are also very sensitive. They get excited by acoustic waves quite easily. And that's actually something that we can see here in this movie. Here, I will explain that very briefly. We have it's called a Rubens tube. The tube is full of fuel, and it's just lit, so we have a lot of flames. Then this tube will be excited by a loudspeaker, And that loudspeaker is actually connected to the piano. And what we see here is that the sound is creating the standing waves inside the duct, and that's actually modifying the shapes of the flame. So this clearly shows that yeah, flames are very sensitive to acoustics. And that has many implications in terms of modeling. Oh, sorry. Why is that? Is because we don't have the flames just by themselves. They don't create this monopole. What we have are flames inside a tube in the combustor. So this is a simplified diagram of a combustor. The combustor, I haven't shown any good diagram, but it's actually just a hollow tube. In one of the ends, there is the flame. The flame normally is stabilized by a black body. So it's anchored the flame to the black body. There is swirling. And then on the other side, we have the, if we are talking about gas turbines or turbofans, as I mentioned before, we have the first row of the turbine. And what happened is that, as we mentioned before, unsteady heat release produced by the flame is a source of direct noise. That direct noise propagates inside the combustor, reach the turbine, and there is a component that is reflected. Another component propagates, and actually that's the one that is interesting for us, the exhaust noise, because that's going to contribute to the combustion noise that we can perceive outside of the aircraft. But the reflected component is also very important. Why is that? Is because, as I said before, flames are very sensitive to acoustics, so they get excited. They generate further direct noise. So if we want to model direct noise, it's complicated, not only because modeling flames is hard. I mean, there is chemistry, there is turbulence, but also because we need to keep that coupling that happens inside the combustor. The acoustic modes of the combustor are very important. And that feedback is important. In fact, it's so important that for certain design points, or for certain design points, this two-way coupling between the acoustic waves and the heat release may create what we call thermoacoustic instability. Thermoacoustic instability are very large amplitude oscillations of the pressure field. And yeah, they are, as I said, they are created by this two-way coupling between acoustics and heat release that can become unstable. They can cause severe damage to the combustor. This is an example here. So this is new burners, and those are burners after an instability. So it is very important to predict and suppress thermoacoustic instabilities. Part of the research that we do is to develop new models for thermoacoustic, but here we are talking about a different aspect of that, which is combustion noise. But obviously, thermoacoustic instabilities are not good for the design, but they also, if you trigger thermoacoustic instabilities, they could create a lot of noise. So obviously, you want, for many different aspects, you want to avoid them. Okay, so that's about direct noise. What we said is that flames are a source of acoustics. Also, they are very sensitive to acoustic waves, and that coupling needs to be well predicted in order to predict combustion noise. And now I will talk about the second component, which is called indirect combustion noise. So the flame, as I said, is a source of acoustics, but also generates flow inhomogeneities that we call entropy and compositional inhomogeneities. So very quickly, just to mention what are compositional. So entropy waves are they're also called hot or cold spots, and they're actually regions of the flow with a different temperature than the surrounding. So you have a flame, that flame burns unsteadily, so there might be pockets of air that has a different temperature than the surrounding. And those pockets of air, they are just going to advect within the combustor, and they are going to reach the end of the combustor at the end. Compositional inhomogeneities is similar. So we have this unsteady combustion, and we might have pockets of the gas with a different composition. The reason for that is that you might have in certain regions a combustion process that is not complete, and you might have a region with more fuel and oxygen than CO2, for instance. And that's also a kind of fluctuation that flames generate. They will create what we call indirect combustion noise. And I will explain you in a second why is that. So as we said, the acoustic waves generated by the flame, they just propagate in the combustor, but the entropy waves and the compositional homogeneities that I mentioned, they are just going to be swept downstream. They are going to be advected by the mean flow. And if they are in a non-accelerating flow, they are silent. So they don't generate noise. They are just passive. One more thing before we move on is that this component of combustion noise is called indirect combustion noise, which is generated by entropy and compositional homogeneities. But because entropy waves are the main source of indirect combustion noise, we use the term indirect combustion noise and entropy noise in this commutable. So from now on, I'm going to use entropy noise to refer to indirect noise. Okay, so as I said, if the flow is non-accelerated, these hot spots, these entropy waves are silent. But then what is entropy noise? So we know that when the flow is accelerated, acoustic and entropy waves become coupled. And that means actually that when you accelerate those entropy waves, acoustic waves are generated, and thus acoustic waves is what we call entropy noise or indirect combustion noise. And we can see that here in that video. Here on top, we have temperature fluctuations or entropy fluctuations. And we see that when they are advected, nothing happens. So here we have the pressure fluctuation, so this is the acoustic field. And the moment that they are accelerating, we generate an acoustic field. We generate this dipole along the nozzle. And this noise is what we call entropy noise. Okay, so that's combustion noise. We have direct noise and indirect noise produced by flame, by unsteadiness of the flame. But how do we model combustion noise? Okay, so to model combustion noise or try to understand is difficult computationally. The reason for that is because the combustion noise or combustion itself involves a very large range of length and time scales. So for instance, the flame has tiny length scales because of the turbulence and the flame chemical reactions. They happen in very, very narrow regions. But however, the acoustic waves, they have very, very low frequency. So they have very large wavelengths. So this is expensive from a computational point of view because you have those scales. Also, if we want to model combustion noise, we will need to simulate the chemistry inside the combustion chamber. Then we'll need to simulate all the blades of the turbine, all the elements of the turbine, the rotors and the stators. And finally, we'll need to propagate that noise to the far field. So that's a very expensive problem if we want to do that numerically with high fidelity simulations. So how can we model combustion noise? Well, we can borrow an approach that is used to predict thermoacoustic instability, which is a multi-scale treatment. So what we do, what we do actually is that because the difficulty is in the large disparity of scales, we make use of that and we propose a multi-scale treatment. And we treat separately the acoustic waves and the flames. For the acoustic waves, we use analytical models. So when I say acoustic waves, is the waves propagating inside the combustor and also the waves propagating in the turbine, and also the indirect noise generated by the turbine. For the flame, we are going to use high fidelity simulations, CFD simulations, or we could also use experiments. But the idea is that all the computational resources or all the experimental resources are going to go towards modeling the flame. And then for the acoustic waves, we are going to stay sort of cheap. And then once that we have these two elements, we combine them and we obtain what we call a coupled prediction. And this approach is used as I mentioned before, to predict thermoacoustic instabilities, but it could also be used to model indirect combustion noise. Obviously, there is something missing. So for thermoacoustic instabilities, we only care about the acoustic waves that stay inside the combustor. So we don't model the component that is going downstream towards the exit, and we don't model the propagation to the far field. So if we want to use those models or those methods to predict combustion noise, we'll need to new models for the acoustic propagation across the turbine and also to the far field, but far field usually is easy. And also I would like to mention that the current models that we have or are available for entropy noise are very limited. So if you want to compute combustion noise accurately, you need to model it to sources, direct and indirect sources. So you need good models for entropy noise. So based on that, we did some work actually. And what we're trying to do is to develop entropy noise models for blades. That's the final objective. Right, so in industrial combustor, I showed you before the concept of entropy noise in a 1D nozzle, which is slightly simplified idea. In gas turbines, it's slightly more complex because the flow will go undergoes a rapid acceleration through the combustor and the first turbine stage, and is heavily rotated and accelerated. And there is where entropy noise is going to be created. As I said before, with a component propagating upstream and another component going through the turbine. Yeah, new models for this entropy noise are necessary, both for thermoacoustic and for modeling of combustion noise. But the problem is that only zero frequency approaches, only zero frequencies models are available. This is a very old paper from Kamsey and Marvell. I have to mention that this is actually not true anymore. When I wrote this paper, this was the state of the art, but last year there were a couple of nice publications extending this zero frequency theory. Okay, but let's see the approach that I use. So we were trying to develop these models for blades, entropy, noise, interacting with blades. And for some reason, we thought that it would be easier to start with just a single blade, develop a model for a single blade, and then move to cascades. At the end, actually, it proved that just models for one blade are harder to develop than for a cascade. But well, we managed to obtain a model. And just to show you how, or the configuration. So here we have temperature. Again, we have a hot spot and an entropy spot. Here we have the pressure, so acoustic field, and we are going to leave this perturbation. This is perturbation temperature and perturbation pressure. So we remove the mean. And what we see is that when this hot spot interacts with the blade, an acoustic field is generated. We see first at the leading edge, there is this wave that is going to be shed now. And then when the hot spot goes through the trailing edge, it creates a second wave, and then it just convects. And again, when the entropy spot is just convecting, there's no more noise generated. So the idea that we had at the beginning is try to model this and then move towards cascades. And that's what we did. So to do that, we use this approach here. So here on top left is the configuration that we used. So basically it's one single airfoil at an angle of attack with a given chord with a wake. Then there is a far upstream, there is a uniform mean flow. Obviously that mean flow goes through the airfoil and yeah, there is a flow that is developed around the airfoil. And then actually on top of this uniform flow, we impose an entropy fluctuation, okay? And what we are doing is we impose these entropy fluctuations. We leave this entropy fluctuation convect. The entropy fluctuation will interact with the profile, and that will generate an acoustic field. And that acoustic field is what we want to obtain. To do that, we have the following assumptions. So we assume that the problem is 2D with a 2D mean flow. So why do we have that assumption? So if we go back to the here, so this is the turbine. So what we can see is that the radial, in the radial direction, the length of the blade is very small compared to the other directions. So we can actually, so the modes in the radial directions are going to be cut off, and we don't need to model them. Okay. Right, so we have a 2D problem. And then we assume that the flow is compressible and inviscid. So those are typical assumptions of acoustics. And then we assume that this entropy fluctuation is small compared to the mean flow, and also the acoustic field that is generated is going to be small compared to the mean flow. If we do that, we can linearize the problem, and we obtain the linearized compressible Euler equations, which, without any further assumption, we obtain that. But it's difficult to work directly analytically with the linearized compressible Euler equations, especially in 2D. So what we did was to recast those equations using this splitting. So this is what is called rapid distortion theory that was introduced by Goldstein. Just to mention that we extended this theory to account for compositional noise. That's still not published, but we have a proceeding. If any one of you is interested, I will be happy to direct you to that. But the idea of the splitting is the following. So we have, this is the acoustic velocity, and we split it in 3 parts. There is one part that is an acoustic potential. Then we have a part that has to do with entropy. And we have a component that we call homogeneous component. It does not have any physical meaning. And then the pressure field can be retrieved from the acoustic potential field. Okay, so if we introduce this in the linearized compressible Euler equations, what happens is that the equations are going to become, so the 4 equations coupled are going to become these 4 equations here. Here we have the entropy equation, which has an analytical solution. We have the equation for the homogeneous part that also have an analytical solution. And finally, here we have a wave equation with a very complex source term. But the advantage of this approach is that we solve this equation, and then we can evaluate the source term and solve the wave equation. So it's a much simpler formulation of the equations if we want to develop numerical methods, analytical methods. Right, so we want to solve this equation here. And to do that, we make a further assumption. So we assume that the blade is compact with respect to the acoustics, but not to the entropy perturbations. The mean flow velocity is the deviations to the mean flow velocity are small in some sense, and we apply what is called the Born approximation in frequency domain and use a Lorentz type transformation. And what we do is that we can transform this equation into the Helmholtz equation, which is wonderful because there are many analytical tools to deal with Helmholtz equation. And we decided to use the Green's function approach. And what we obtain is a solution for the acoustic potential given as a superposition of a monopole plus a dipole in the horizontal direction and a dipole in the vertical direction. And then from this potential, we can retrieve the pressure field. Okay, so before we, so that's actually what we did. We obtained that analytical solution. But before we do that, we need a reference case to validate the model. And for that, what we did is we did numerical simulations of the compressible linearized Euler equations. For that, we use an in-house solver that I developed myself. It's based on discontinuous Galerkin, frequency domain implementation, and it has a perfectly matched layer for the non-reflecting boundary condition. And this is the kind of simulations that we obtain. This is the reference to the paper if you want to look. But those are here we have the density. So this is actually the entropy wave or a proxy for the entropy waves. And upstream, we assume that the entropy waves is plane. It's a plane wave. This could be very easily extended to non-plane waves, but here we are restricted to plane. And here we have the acoustic field. So we see that the entropy fluctuations are just advecting, and the result is that we have this acoustic field that is generated that looks sort of like a dipole in the horizontal direction. Okay, so those are numerical simulations. Oops, sorry. So let's see how these simulations compare to our code. So those are the results for 2 Mach numbers, Mach 0.1 and Mach 0.2. We are giving the results here for a given frequency that is given in a non-dimensional form as a Helmholtz number, okay? And then those are directivity plots. And basically what we do is we put an observer that is like 7.5 chords away from the airfoil, and we compute the directivity, we compute the pressure. Just to mention that here we are talking of the absolute value of the pressure or the pressure RMS. There is no decibels involved. There is no conversion to decibels. So the agreement is actually very good. And here what we can see is that dashed line is the computational simulations, black line is the model. So what we observe is a really good agreement between simulations and the model. So we were very, very happy with this. Obviously, when you go to higher Mach numbers, it's not working. It's working slightly worse, but not that much. And we could even go to we've tried Mach number of 0.7 and it's still working. We capture the directivity well. All those details are in the paper if you're interested. Right, and that was the model that we create, but also we had some more work. We have done more work on how to extend, how to model cascades. This is using also the Goldstein approach, rapid distortion theory, but the solution method is different. And this was a part of collaboration with Lorna Ayton and Peter Badu, who are at Cambridge and MIT, respectively. Here again, entropy waves, the acoustic field. In terms of future work, because this model is only valid for thin. We have what we call a thin airfoil theory, so thin blade and very small angle of attacks. And our idea, what we would like to do is in the future is relax this thin airfoil assumption, and we would like to consider airfoils like this that are more realistic, that have a thick. They are thick and they have a strong angle of attack. And for that, we would like to, we are planning to use a semi-analytical extension of this approach. As you can see here, the acoustic field is more complex. You see how the entropy wave is stretched in many directions, and there is this sort of rotating dipole field that is created. Okay, so that's about modeling combustion noise. And now I will talk about how to reduce combustion noise. I don't have too much time, so I will try to be quick here. And how to reduce combustion noise? Well, we have already in the combustor, we have acoustic liners. So, I mean, this is a rocket engine, this is a plateless fan, and this is actually the aeroengine itself. But what we can see is that we have this method to reduce noise where we have a sheet, metallic sheet, with a lot of micro perforations. And this for this application is to reduce noise, but for aeroengines, they are mostly there for cooling. They create a layer of cold air close to the material, to the wall, and that's protect the wall. However, they provide a very valuable acoustic damping, and that's actually going to reduce the propensity to thermoacoustic instabilities, and it's also going to reduce combustion noise, at least direct combustion noise. For indirect combustion noise, it's going to be harder, and that's actually an open direction, but for direct combustion noise, we can use liners. And our idea is to optimize those liners. So before I move out how to optimize the liners or anything else, I just mentioned the way, a typical way to model those perforated plates. So what we do is we cut the liner and we model it as a flat sheet. And then what we do is that if the perforations are sufficiently separated, we can just model one of them. And we can use numerical simulations to model one of them, for instance, or we can use models. But the idea is that at the end, we extract an impedance across the perforation, and then we can use that impedance to model that wall. So right, just in terms of how we model this. But what are we going to do? We are not in this work, we don't care that much about how to model, but we care about optimizing. And I will explain you now how. So just to mention, well, this is, as I said, this is the typical configuration that we use. And we did that. Actually, we did simulations of this configuration where we have one duct upstream, one duct downstream, and a perforated plate. And a perforated plate, sorry. And we ran the simulations of this to characterize the impedance. And what we did is we ran 3 simulations, one with a sharp hole. So here the corner of the hole is sharp, one with a sort of chamfer upstream, and one with a chamfer downstream. We ran the simulations with a code. I will go into the details later. But the idea is that when we look at the acoustic energy that the perforation absorbs, we saw that the chamfers modified hugely the amount of, this is the acoustic absorption coefficient. It modifies greatly the amount of acoustic energy that the perforation can absorb. So these sensitivities inspire us to do optimization. And that's what I'm going to do now. So the aim of this part of my presentation is to develop an optimization tool that can be used to design bespoke hole geometries that can be used in industrial applications to reduce noise, with an application obvious, which is to combustion noise. And for that, we will use Bayesian optimization. So as I said before, but again, just very quickly, this is the configuration that we have: an upstream duct, downstream duct, and in between we have a plate, and we have a perforation. This has so this is an axis of symmetry, and this will be axisymmetric. So if we look at the cross section, probably that wasn't clear before, but if we look at the cross section, this is going to be a circular cross section. So this is duct, circular duct, and this is the circular orifice. Okay. And what we do is we make the following assumptions. We assume that there is a steady bias flow that we impose at the inlet, left-hand side, is mean flow. If we do that, the flow will be determined by 5 non-dimensional parameters: the Mach number inside the hole, 3 geometrical parameters, and the Reynolds number. We are going to assume that the Mach number inside the hole is small. This is very typical for this kind of industrial liners, and the Reynolds number will be high enough, so we have turbulence. Okay, so we solve for that using this approach. So we solve using the incompressible run simulations, using OpenFOAM, K omega SST turbulence model. And what we observe here is that the flow comes from left to right. When it reaches these edges, it separates, creating this recirculation zone. And then, yeah, it remains detached. And here in the center line, there is a high-speed jet, in a sense. Okay, now on top of this mean flow, we can impose acoustic perturbations. So what we are going to do is we are going to impose an incoming acoustic wave. Okay, that is going to be time periodic and is going to have a small amplitude so that we can linearize. And what we want to do is we introduce this incoming acoustic wave, and we want to obtain these outgoing acoustic waves. And the acoustic response of this system is going to obtain as the solution of the linearized compressible Navier-Stokes equations. We have computed that with an in-house solver that is implemented in frequency domain. And as I said before, the objective is we introduce this incoming acoustic wave, and we want to compute the reflection and the transmission coefficient. Okay, so we validate the approach, and for that we compare with numerical results of Lacombe et al. This is the transmitted way, and this is the reflective way. Linear Navier-Stokes, an experiment, and we see a very good agreement. This kind of agreement is good for this kind of applications. And I'm presenting those results in terms of, again, a non-dimensional frequencies that I give as a Struhal number. Okay, so this approach is validated. Now let's optimize this. So to optimize, we are going to use the absorption coefficient. The absorption coefficient, basically, it computes the energy of the incoming waves minus the energy of the outgoing waves divided by the energy given to the system incoming. If it's equal to 1, it means that we have perfect absorption. So we are absorbing all the energy of the system. If it's equal to 0, means that we are not doing anything. So we are not absorbing any acoustic energy. And if it's negative, it means that the perforation is going to generate acoustic energy. This is what we call whistling. And it's exactly the same process that happens when you whistle with your lips. In this case, I'm creating actually acoustic energy from vorticity. I'm creating that acoustic energy as a whistle. So here we have the diagram for that hole. This is the absorption coefficient that we compute. We see that at low frequencies, we can actually dump 50% of the incoming acoustic energy, but then it rapidly drops, and at this Struhal number, we have whistling. So we have a region of whistling here, a second region of whistling here, and here the absorption is not really good. It's around 20%. Okay, so we want to optimize that, and for that, we are going to use the chamfers. So we are going to introduce 2 45 degrees chamfers, so one downstream and one upstream. And we want to maximize the absorption coefficient. So basically, we want to find the size of these chamfers, the one upstream and the one downstream, that maximize the absorption coefficient. Okay, so how do we do that? So first of all, we take the absorption coefficient at this frequency, Struhal 1.3. Why? This is because the peak of acoustic energy generation, it's very, very, very bad. Actually, it's generating a 50% of acoustic energy. And we are going to, using this the absorption coefficient at this frequency, we are going to optimize that using Bayesian optimization. We run the algorithm, and what we obtain is the following configuration. This is the optimal configuration after 300 iterations. And what we can see here is that upstream, the chamfer at the upstream is very, very small. So probably this is not converge because probably it should be 0, theoretically. And the chamfer downstream is very large. So actually, in terms of physics, this behaves as a very, very thin hole rather than a hole with a thickness. But what we can see is the absorption coefficient is increases from whistling. So instead of creating a 50% of acoustic energy, now it's going to extract almost half of that acoustic energy. So this is a huge improvement. And now let's look at that in terms of frequencies. So again, blue is the straight case, no optimization. And the black squares are the optimized chamfer. And we see that we are not just removing completely the whistling. We are just actually having a flat region here with a 50% of acoustic absorption. And we are mostly improving all the regions, or we are improving the absorption in all the frequencies. Okay, so that's in terms of optimizing perforation. So this is a technique that could be used to reduce combustion noise. We could, holes that are already there, we could optimize them. Yeah, let me now finish this presentation with some conclusions. So the conclusions are the following. So combustion noise is potentially the next noise barrier for commercial aviation. That is, if we consider traditional architectures and traditional fuels, but also if we consider the new approaches, hydrogen, for instance, or supersonic aviation. To model combustion noise, we could use a technique that we borrow from thermoacoustic instabilities that are multi-scale approaches. But in order to do that, we need to improve the models for the entropy noise or indirect combustion noise, and we need to improve the models for the downstream propagating of sound across the turbine. And what I have presented here is a model for the entropy noise generated by blades. I have also presented that we can reduce combustion noise if we use optimized acoustic liners. In terms of future work, we would like to extend our work on entropy noise to realistic cascades. So that's actually cascades, not just cascades, but cascades that are thick. We would like to develop models or a modeling tool that can predict, that can actually go from flame to the far field. If we change the fuel, we could actually know what happens in the far field to combustion noise mostly. Before I finish, I would like to thank to my collaborators. So first and most important is Professor Amy Morgan. So she was my PI when I was a postdoc, so I was working for her. But also I would like to thank Dr. Dong Yang, Dr. Saikumar Yedula, and Dr. Renaud Gaudron. Finally, so I have just presented a small snapshot of the research that we have done on this, but we have a few other papers that I would like to advertise along the same lines, actually. Here we have a quasi one-dimensional solution with heat transfer. So this is a very powerful solution. Actually, it can model quasi 1D flows with heat transfer for any kind of, for any Mach number and for any frequencies. We have also looked at what happens when you have entropy waves that are decelerated at sudden area expansions instead of nozzle, and we found very interesting results there. Finally, we have some interesting results. If you're interested about the acoustic liners part, we have investigated a new range of perforations where the flow actually is not always separated, but it reattaches within the hole, and we found some interesting results there. Finally, here, this paper is linked to this one here. We have a modeling approach for sudden area expansion. So it's we develop a model that accounts for both. Yeah, that's it. Thank you very much for your attention. And if you have questions, I will be very happy to answer during the Q&A. Okay, I will actually leave this here. Q&A. Okay, so we don't have any questions at the moment. Right. So, okay. So I'll read the question. So the question is from David Chapman. Thank you very much for the question. And he asks if does it matter what phase of the perforation are chamfer, the inner or outer part of both? And actually, the answer is that it has. It doesn't matter. It has a strong effect. So, for instance, you can see here. So, if you have a very tiny perforation, as we consider here, this is the upstream chamfer, so that would be the inner, and this would be the outer, or other way around. And actually, what happens is if we look at the acoustic absorption coefficient, the chamfer downstream and the straight case, so there are changes. We can see changes and they are clear, so it's sensitive. But if we compare the sensitivity of the downstream chamfer to the sensitivity of the upstream, the difference is huge. So I would say that the perforations are much more sensitive to chamfers upstream. But that's for holes that are very close to the straight. If you are moving to larger chamfers as the optimal solution, we saw there that it was optimal actually to put a chamfer downstream. So if you have, if you want to add just a small perforation and you want to have a huge impact, I would say go for upstream chamfer. If yeah, okay, so that's it. Okay, so I have a comment from Charlie Birch. Fascinating work. Thank you very much. Any more questions? Right, so I have another question is how are the acoustic liners incorporated around the combustion area? So let me show you this slide. Right, so let's see if there is. So the idea is that the, well, I mean, let's go. I don't have any good image that I can use. Yeah, but the idea is that, one sec. The idea is that so as I said, so the combustion chamber is just a hollow tube, right? With a flame at the one of the sides there is the flame, at the other side there is the turbine, and there is a wall around. So that wall itself is the wall that is perforated. That's what we can see here in this image. So that wall will be perforated. Outside of the wall, you have cold air coming from the compressor. And because that air has a higher pressure, it will go through the perforations. And because that's cool, that's cold, and the gas inside is hot, you create that small layer that protects. So the answer is just that, is that it's the liners are already incorporated in the walls of the combustor. Okay, so the next question is for entropy noise. What are the reference values used for scaling normalizations? So here, so if we're talking about this, we don't have any. So those are okay. Here, everything is normalized by density and speed of sound, which means that the pressures, because those diagrams are for pressure, the pressure will be normalized by the mean pressure, well, gamma mean pressure. And so basically we are working everything normalized, as I said, gamma pressure, and the entropy itself is just, the entropy is normalized by CP. You divide the entropy fluctuations by CP, that's already non-dimensional quantity. Yeah, but the thing is that the magnitude of those values is not really relevant, I would say. So this is, so we are not expecting that just a single blade generate that much noise. And also the observer is a bit far. So in order to have a meaningful comparison, we should probably compare in terms of energy. And also, like, as I said, this kind of, we don't expect much entropy noise in this specific example that we use to demonstrate the method. But yeah, and also something to mention is that entropy noise scales with Mach numbers. So if you go to Mach number close to 1, we generate much more noise. So you can see, I don't have the results here, but you can see that in the results. Okay, anything else? Oh, okay. Okay, so next question is from David Abbott. For perforated plates, what whole Mach number is appropriate for good damping? Password by Dowling indicated that damping would be low at Mach numbers typical of GT cooling flows. Yes. So in terms of Mach number, so the thing is that for those, because the Mach number will be small, we're actually, so the Mach number inside the perforation will be small, so we are neglecting. So for instance, for the mean flow, we are using incompressible simulation, so there is no effect of Mach number there. And for the acoustics, actually, it shouldn't have much. It shouldn't have too much influence, but it's going actually to change the. Probably it's going to change the region. It's going to change the scaling in frequency. Probably, it's the only effect that I can see from the Mach number, because you will be scaling, so your graphs are going to collapse with the Struhal number. But yeah, if you have different Mach numbers, you could move that to different physical frequencies. Is my only sort of guess. Okay, so since there are no more questions, I will wait 1 more minute just in case if there is any final. Oh, actually there. Oh, okay. Mach numbers are about 0.2, which is not really small. Inside the perforation. Well, honestly, I don't know. I mean, that's so. I mean, in the numerical approach that we are using, obviously we are neglecting it. I think Mach numbers. So the numerical approach. So I think in terms of the Mach number plays a role in the mean part and the perturbation. For the mean part, still Mach number 0.2 is not going to. We're not going to have compressibility effects. So the mean flow is going to be very, very similar already. So I don't see, and it's not. I believe it's not going to have an effect there. For the acoustic part, the perturbation actually. We don't have constraints. So for the perturbation part, we don't have constraints. We only assume and we are actually replacing the energy equation, but the entropy equation, and neglecting it. So we assume that there are no entropy fluctuations, and that approach is actually quite general. So even for Mach 0.2, I mean, this approach should work. But in any case, I mean, like Bayesian optimization that we use here, I didn't put the details, but Bayesian optimization is very nice because you can just wrap it around any numerical tool. So we could replace, for instance, our compressible, the incompressible simulations from OpenFOAM for the compressible solver. And then for the acoustics, we could add the energy equation. It's just going to be slightly more expensive numerically, but yeah. Okay, thank you. Okay, so I think that's probably it. I'll wait 1 more minute just in case. Yeah, and then if there are no more questions, finish. Okay, so it seems that there are no more questions. So thank you very much for attending this presentation. If you have any, I didn't include my email in the slides, but if you have any questions, please send me an email. Yeah, thank you. Yeah, I wish you a lovely day. Yeah, take care.